So homework was to implement the block, whatever flippy thing. We already put it into the parser, right? Oh, so we have to put it in the parser, and then we also need to, oh, there we go. So put it into the parser and also apply expression. All right, so putting it into the parser is going to be easy enough. But then applying the expression, we're going to have to make a decision. What do we want the output of a block expression to look like? A couple different options we can go that way, but let's put it into the parser here first. Down here, do we decide kind of what it's going to look like? So we're going to have something that looks it's going to be a list containing some things. We're going to have to put something in the front to say that this is what this guy is. Otherwise, is anything that's just a list of expressions. Let's look at our parse. All right, so in this case, we're looking at if the car is a define or a plus plus or a minus minus or a repeat or an or an XOR or an and. These are all looking at the cars of it. So really what we can do, let's see, oh, our else is, it must be a let expression, but a let expression for ours starts with a let, right? So what we could do is we could steal this guy and say if the car is a let, do the let stuff. Just back this off here like that. All right, so if it's a let, do the let stuff, and then throw in a new else and treat the else as it must be a block expression. So you could do that, or you could have said that our syntax is going to force them to maybe put the word block at the front of the syntax. Either one is acceptable. At some point, you're going to only be able to have one else. So depending how complex your language gets, you get to make the choice whether your else is going to be that block expression, or maybe you just say an else means an error. You didn't give me reasonable syntax. But for right now, given what we decided last time is a reasonable way of showing a block expression, which is a list containing expressions, right? This is a list whose car is not an or any of those other things. Now, doing it this way, it does give us the requirement that our list does have a car, which means that in this case, a block expression could not have couldn't be the empty list. That makes sense? We actually have to have a real expression in there. Because if we would ask for well, I guess we could ask the question, because we could create an empty block. We just wouldn't want to process it through parse expression unless we had a block. Actually, we can do this pretty easily, actually. Okay, this would be a fun one. So if we're in this else, that means we must be dealing with a list of 0 or more expressions, right? And what do we want to do? We want to what do we want to do to each element of that list of expressions? Call parse expression on it. So could we use map? Couldn't we map parse expression across that list and then tack on our, so we'll have a list containing all of our parse expressions and then tack on the, what do we call it, just a block exp. So we would do something like a cons block exp onto the result of map parse expression onto the expression that was passed in. So the expression that was passed in should be a list of expressions if we're in this else, right? And we'll go ahead and map parse expression across that, which should apply parse expression to each of those expressions. Should give us then a list of parsed expressions. And then we'll just cons onto the front of that list the word block expression. All right, so let's test that here real quick. Did we already add a define to our language? We did that last class, right? Yeah, we have a define. All right, so if I pass it something like, that's our example thing, right? And then we call parse P1, we have our scope, blah, blah, blah. I'm just not going to apply the program yet. Let's just look at our parse P1. This should give us a block expression whose first thing is a define expression, whose second thing is a var expression. Let's see if our map thing is working. Did only one expression. Oh, sorry. This needs to be a list of these things. Yeah, see, I think our challenge is always going to be writing syntax in our made-up language, right? It's almost always the problem we run into is how do we properly write a program in the language that we invented? All right, so here's our parsed program. So we have a block expression, and this guy has in it, following block expression is, here's our define expression, and here's our var expression. So does that look legit? That's what our parsed block expression should look like. All right, so that was fairly easy to do it this way using map. So map made this shorter. Otherwise, what did you do? You had to just check to see, is the list null? If it is, return the empty list. And otherwise, cons onto this parse expression of the car onto parse expression for the, actually, you'd have to treat the rest of it like a, well, no, and you call parse expression on the, ooh, that would actually get kind of nasty, wouldn't it? Because you're going to have to create a loop of things to go through that list. Probably a helper function would have been the easiest, because you're effectively taking a list of expressions, and as long as you still have an expression in there, you want to call parse expression on that guy. Yeah, so this is way easier. Calling map on this, because effectively what you had to do is you had to write your own version of map to make it work. Okay, so does anybody want to see that alternate approach? So everybody did it with map? You all did it the hellish way. All right, so we have our block expression then. All right, so now we need to decide, if I have a parsed program that looks like this, what is reasonable output for that guy? Okay, now up to this point, what have we been doing? We've been returning two lists, right? Where the car of the list is our answer, the result of the expression, and the catter of the list is the resulting scope stack, correct? So now, one thing we could do is you could return a list of two lists. So maybe the most straightforward way of doing this would return a list of two lists, where each two list is the result of that particular expression, as well as the resulting scope stack from executing that expression. Now, what probably makes more sense if we think about going through a Java program. So I have a, well, we can just use this. Okay, so if I'm going through a Java program in here, let's just look at main activity. You know, I have some variables in my scope. I'm setting a variable here, so the result of this guy is a scope with a little bit more stuff in it. Here's another, then the result after this line is an even further expanded scope. Okay, then this is even a further expanded scope, and then this is going to call some function. So if this is a block expression, we just look at these four things. This is the first expression, this is the second expression, third expression, and fourth expression. The result of this might be the result of this line plus the result of this line, followed by the result of this line, followed by the result of this line, which is probably whatever update tree count returns, followed by exactly one scope stack, which is the cumulative change across all the scope stacks, or across all the expressions. That's probably what makes the most sense for a block expression to return, is what was the final scope that this guy returned. All right, now keep in mind, we can't use map for this guy to apply the expression. We can't just say map apply expression across the body of the scope stack, or I'm sorry, the body of the block expression, because we're supposed to take into consideration the return to scope stack from the previous expression, because that might have an impact on the next dude, right? As we go down the list. All right, so we could have a couple of different outputs. So one thing we might do, let's just go back here and show two options for our output. All right, so this is our parsed program in our example. We'll just kick it down here. So maybe applying this would give us a list whose first element is a list of results. So maybe this guy is define expression D3. Didn't we change that to return a true last time? So that it returns whether or not okay, so this guy would return a true. The second element of this list would be the result of D, which would be a 3. And then ultimately, the final scope stack for this guy would be that with a D3 tacked on to the scope. Then one last, I'm lost. One last closing parenthesis there. I'm gonna kick this down a line. We'll just put the two scopes on top of each other. All right, so after that block expression finished, we would have the car of our result would be a list of the results. So the first expression returned a true, the second expression returned a 3. And then the catter of our result would be the final scope stack. That was the result of after we called every single expression passing the cumulative scope stack to it. Right? That would be my suggestion on what kind of a useful result would be. Because we don't necessarily need to know what the scope looked like as we were walking through that block. We care from the perspective of correctly executing each expression, but at the end of the block expression, when we see our answers, all we really care about is what was the resulting scope of that guy. That makes sense? Now, we might even say in many cases we don't even care about that, because we might not, because realistically that scope might die at that point. You know, if this is the end of the block expression and we say that a block expression gets its own fresh scope, that scope might actually die with this guy. But what if you have a block expression inside of a block expression? That's not something we necessarily do in Java, but probably when you were first programming, you accidentally put curly braces inside of curly braces like that, and it's not incorrect. You can have block expressions inside of block expressions. People just don't do it directly. We indirectly do it by putting like a for loop inside of a block expression, right? You've put for loops inside of functions. So you have the opening and closing curly brace and then of the function, and then you have the opening and closing curly brace of the for loop. So that's a block expression inside of a block expression. They just happen to be attached to either a function or attached to a for loop. All right, so this is one thing we could do. Another thing we could do is have a list of results. So an alternative thing might be, I'm going to steal this. So this closes the whole thing. This closes that scope stack, right? So this will be a little redundant, but still accurate. So I'm going to have a list, and this list is going to have in it a bunch of to lists. The first to list would be the result of the first. So that's the result of that first define statement. And do I have this in the right spot? Let me undo this real quick. So yeah, so this should be a standalone guy there. And then the second element would be a to list containing the result of the second expression, which would look like that. So this might be the result of a block expression where you have a list containing all the to lists that were the results of the expressions inside of it. Ultimately, the very last to list, the scope stack associated with that, is our resulting scope stack. So we still have that information. We just have verbose information along the line telling us showing us how our scope may have been changing along the way. All right. So both of these are the same answer. We just are giving more verbose information up here. Do we have a preference, what we prefer? How many of you did it more like this, where it was a list of to lists as your result? We have a nod and no other. How many of you did it like this one, where we have a, where am I at here? Like this one, where we have a list of results followed by just the scope stack? How many of you did it a completely different way? All right, how did you do yours? What was your result?
I think we boiled down to whatever the last statement was, and then just spat out the scope stack.
Okay, so.
Which isn't really, I mean, because maybe the last statement doesn't boil down to anything, maybe it's a define or something.
Okay, so in your version of this, you wouldn't have had the true? We would have never seen that?
Right, we weren't keeping track of them.
Okay, so you went through, you had the final correct, the final last answer, proving that the scope stack was changing, but you didn't give us the answers along the way.
Right.
Okay, but you still proved that the final result was right, so you could have given the answers, you just didn't cons them on. Okay. That's probably not the best approach for us at this point. We probably want to see the results along the way. So actually that's all of our extremes, right? So his extreme is, I'm going to show you the last answer in the final scope stack. The other extreme is, I'm going to show you all the answers in all the scope stacks. And then maybe the middle of the road is, I'm going to show you all the answers and only the final scope stack. Pick your poison, but probably that one's the worst one. I think you want to see all the answers. I mean, if you think about a Java program, we have something like this. We care if these were all print statements, right? We want to see those outputs, right? We'd like to see print this, then this, then this, then this. We don't necessarily care about seeing the scopes after each of those, but we definitely want the scope to have changed. All right, but as long as your final answer is correct based on changes in the scope, then you did the right logic. Your just output was formatted the way you decided you wanted it to be formatted.
I think giving each resulting scope stack might be helpful down the line for us to be able to tell what's going on.
Yeah, definitely from a debugging perspective.
Yeah, it's like kind of having debugging.
Yeah, and it actually is probably going to be easier to write that way too. Otherwise, you're going to have to do a whole lot of kind of like dismantling and then throwing it back into something, because you're going to be consing the cars. of the result together to give you a list of results, and then but then still needing to get the catter to pass it into the next apply expression for the environment that expression in which that expression should be evaluated. So in any case, let's do it that way first. Let's call that our most verbose solution. And then if we decide we want to squelch the number of parse stacks or what do we call it? Scope stacks. See, we're getting a little tongue-tied with our language now, right? Get to this final exam, and the questions are just going to be like basically encrypted, right? Don't even know what you're asking anymore. Give me the third scope stack in the stack of scope stacks. But I'll enjoy every minute sitting up here. I should make chili and bring it with me and just.
Write a question where you have to get what the actual question is based on
convert the question to English.
You should ask us a question about Skyline chili.
Yeah, but only you would get that right, probably. Has anybody else in here actually ever eaten Skyline chili? So only you and I know the secret. I guess that works out well for you.
Yeah, it does. And you get to see them all in pain.
While I'm eating Skyline chili. Oh, yeah, so good. Doesn't even make sense that it's that good either.
It doesn't.
There's nothing special about it. Who puts chili on top of spaghetti and then a pound of cheese on top of that and expects it to be something amazing?
Oh, the best is the time of year when they double up the cheese.
Oh my God.
Yeah.
I can't even imagine.
It's
it doesn't even stay on the
it
plate.
goes from this high to this high. It's ridiculous.
That's amazing. I'm going to need one of those lasagna pans. That way I have walls to catch the cheese because you're going to lose that. All right, so let's write this, dude. So we're going to be adding this to our apply expression. And actually, we don't have an else in our apply expression, correct? And that's actually okay because our apply expression is working off of our parsed. So we always have a car that tells us what this dude is. So really an else would just be an error message printed out. Okay, so this is that guy. So all right, so that's the end of that piece. So now we'll do an EQV get parsed expression name from parsed expression if that guy is equivalent to block exp, then we'll do our block exp stuff. All right, so block exp stuff is going to say I have a list of expressions, and that list of expressions is contained after the block expression, after I peel off the block expression. So it's going to be the cooter of my parsed expression will be the list of expressions, correct? And that might be the empty list. So if we want to, deal with this maybe in a smaller piece here, I'm going to go ahead and I'm going to create a let. I'm going to kick this down a line, actually. So we're going to say let list of expressions. This guy is going to equal the cooter of parsed expression. So the cooter of parsed expression, this is our parsed expression as we're looking at it in there. The cooter of that guy would be the list containing, in our example here, those two expressions, right? So it's going to be a list of parsed expressions. So here's our list of parsed expressions. Let me just get some space here. And actually, just so we're verbose here, list of parsed expressions. We already have big, long variable names anyways. Might as well just roll with it. Okay, so we have a list of parsed expressions, and that is going to be the cooter of our parsed expression. All right, So now we're in the body of the let. So in this body of the let, we need to apply expression for each of those guys. And we might be tempted to map, which would be nice and easy, but then we wouldn't get the benefit of the resulting scope stack after executing each of those guys. That make sense? All right, so we're going to need, now you could write this as a helper. In fact, initially it's probably going to be easiest to write it as a helper. Otherwise you'd have to use a, well, you wouldn't have to, but you would use a let rec, which we haven't introduced yet. So let's do it as a helper first, and then we'll add the let rec stuff in. So for right now, let me just, I'll just close that there. So our body is empty for right now. And let's go ahead and write the helper. So we're going to do define, apply, is it underscore expression, or no, it's dash. Apply expression block helper. That guy's going to be a lambda that's going to take in a list of parsed expressions along with the initial environment in which we're executing the very first expression. That make sense? All right, and ultimately what this guy is going to produce for us, I think we decided on the list of two lists as our output. All right, so he's going to create a list consing the result of apply expression onto kind of a growing list. So we're just going to keep calling apply expression, passing a potentially changing environment, consing that all together until we finally run out of expressions to apply expression on. So this is our old pattern. So if null list of parsed expressions, go ahead and return the empty list. That'll be the finishing touch on our cons, right? Otherwise, we must have at least one element in there, right? So now here's where things get a little tricky. I need the result of calling apply expression on that first element because I'm going to need that result in order to call my next one. So I need a variable. So we're going to create a let. So we're going to say let result be apply expression. Did I spell that right? Apply expression on the car of, oh, that was the right thing. The car of list of parsed expressions, along with the current environment as far as I know about it. All right, so result is going to equal that. So result's going to be a to list, where the car of that to list will be the answer for that particular expression, and the catter of that would be the resulting scope stack. That make sense? And that's going to be stored inside this variable called result. Okay, so I'm applying expression on the very first parsed expression in my list of parsed expressions, passing it the current environment, that is the one that was passed in here. And I'm going to store the result of that in a variable called result, and that's going to be a to list. Okay, now I'm in the body of the let. What am I going to do with that to list? I'm going to cons result, because we're going to keep the entire to list. So we'll cons that to list onto whatever apply expression block helper returns on the cdr of list of parsed expressions. And now I need to give it the environment in which the next expression should be evaluated, which is the catter of result. Right? We're going to extract the modified scope stack, potentially modified scope stack from result. So Here's our apply expression helper. I'm going to kick this down a line. Here's the first parameter of it, which is going to be a one shorter list of parsed expressions, along with the catter of result, which should be our potentially modified environment. And that's going to be what I apply expression block helper on. And I'm consing my to list that was the entire result onto that guy. So that's the body of the let. That's that, that's that, that's that. So then what are we going to do up here? We're going to call apply expression block helper. So we're in the body of the let. We'll call apply expression block helper, passing it. This guy takes two parameters, my list of parsed expressions and the initial environment. So passing it the list of parsed expressions and env, that is the environment in which they originally passed me here in apply expression. That make sense? All right, so let's test this guy. We'll go ahead and call our apply program on this, and we should get, as a result, a list containing two lists, with the final scope stack in the second to list being our one that, well, they actually both will show the change, but just because of the nature of the one we wrote here. Oh, this is that the weird syntax, right? All right, so here's our 3. So this is a to list. So there's our 3, followed by the scope stack, and we see that it has been expanded with the d is equal to 3. And then our second to list is true with, we need to spell this out better because these are placeholders. So what 3 is a placeholder. That's this guy. So that's a variable for this. I mentioned before that our scope stack in this case is identical, right, for both of them. Our result, when I look at it, where did I write it up here? This is the version we're doing, right? This guy, where we have the same scope. So we have the identical scope stack twice. So what they do in this output, their version of this output, is they define a variable here, -3-, that is equal to our scope stack. So then the final output is actually, here's our two lists. The first 2 lists, the result was true, and there's our scope stack. The second 2 lists, the result was 3, and there's our scope stack. That makes sense, the weird format of their output. If we created a second define, we can probably get a, I wonder if they'll still create, I wonder if they'll create a second variable. So if I create a second define in here, so let's define R to be 13. And then we'll output D, and then let's output ++ R, which should give us a 14. Let's run that guy. Do we not have a, was ++? I'm guessing my syntax is bad for the language. Is that not how we write ++ in our language? Or do we have a bug in our ++? Here, just for this example here, let me just put R here. We've possibly introduced a bug into our ++ at some point. Yeah, they gave us 2 different variables Actually, it's 3 different variables. We have a variable called 13 that is one of our scope stacks. This is the original scope stack. Then we have another variable 25, which is a expanded scope stack with our new RS13 in it, along with our I'm missing a line here. Where's my D's 3? Well, here it is here. Oh, that's the 7. Okay. So this is that's what 13 is. This is what 25 is. This is what 7 is. So the 7 here, that's our R is 13, D is 3, B is 3. And then the 13 is the second half of that guy. That's our second scope. And this is weird to read, isn't it? They try to make it easier. So this is all just given information. So that's not part of the answer yet. This is just saying, here's placeholders for some known pieces of information. Then we'll simplify the result down here by showing you the list of 2 lists. So the first 2 lists are true. We successfully added that guy, and here's the resulting scope. The second guy is true. The result of our R is equal to, what did I say, 13 or whatever? Yeah, 13. Then the next 2 lists is the result of boiling down, was it C or D? D. And then the third is the boiling down of R, which is 13. That makes sense? So this guy appears to work as written. We potentially have a broken other expression. But before we go and debug that, are there any questions about implementation of block expression? All right, so not too bad. Now, what if? Now, we might say that it's a little bit inconvenient to have this dude sitting out here like this. It's kind of, I mean, really our apply expression is not scary enough yet. Don't you agree? It's too trivially written at this point. At a glance, you can just tell what's going on. So it would be our best interest then if we could somehow get all this logic just sucked up into here, right? That would make the most sense. All right, so what we're going to do here, I'm going to show you that version of it. I feel like Annie doesn't agree with this. All right, so we've talked about lets. We've talked about let stars. What's the difference between a let and a let star?
You can define like A equals 3, B equals A.
Yeah, so let star allows you to define variables in terms of other variables that were defined earlier in that let star, where a let doesn't let you do that. You can define more than one variable in a let, but you just can't define them in terms of other variables in there. So then our next upgrade to a let star is something called a let rec. Okay, so a let rec does everything a let star does, but it also allows us to, a let and a let star allow us to define functions. We've never actually put functions in there, but we could define functions in them. But in this case here, we actually need this function to be able to call itself. We need to be able to recursively call itself, and that's what the rec part means. So if we defined a function inside of a let, so let me just give you an example of that before we dive into the let rec stuff. We'll just do this after this guy. So let's say I define let test to be a lambda that takes in a value, takes in an x. And then we'll go ahead and create a let. And in this let, we're going to create a variable called add 5. And add 5 is going to be a lambda x plus x5. So the value of the variable add 5 is going to be this lambda. Make sense? And then we'll just boil down to add 5 of whatever the passed in x was. So this maybe looks a little confusing because I've used x twice. This is a scoping thing. So this x lives and dies right here. This is the x that was actually passed into this function. If it makes you feel better, you can call this guy val. And then we'll say add 5 to val. That reads better to you. All right, so now we're going to go ahead and test this. So we'll call let test. And we'll pass this guy a 5. And we should get a 10 out of this. So there's our 10. Proving that you can define functions inside of lets. But what you can't do is you cannot, well, clearly we could not do something like, let's create another variable in here. B is 5, and then plus xb. We could not do that with a let. So b is a variable that's not defined. Lets don't support that. So we would have to upgrade this guy to a let star, which would then allow us to define this guy in terms of a variable that was previously defined inside the let. Make sense? All right. But what we can't do is we can't recursively call our add 5. So if we change add 5 to a maybe called sum list. So let's get rid of this guy. So we're gonna call this guy sum list, and he's gonna take in a list as a parameter. And what is he going to do? He is going to sum up all the elements in that list. We'll assume it's a list of numbers. So if we call this an LON, list of numbers. So we'll ask our question. We'll say if null LON return 0, else add car LON to sum list footer LON. So that's what sum list is, right? Takes in a list of numbers. If it's empty, return a 0. Otherwise, add the first number to whatever sum list returns for the rest of the numbers. And then inside here, we'll pass it our list of numbers, and we'll call sum list on that list of numbers. So let's call 1, 2, 3, 4. So that's our list of numbers. So we want to get a 10 out of this. It's going to scream at us, this function is not defined. It doesn't know about sum list. So this takes us to the next step, right? Because now we're trying to define a variable in terms of itself. Let stars allow us to define variables in terms of previously defined variables. But now I need to define a variable in terms of itself. That make sense? So I need to upgrade this guy to a let rec. And I have bad syntax. One moment. Lambda LON.
Need a quoting let test where you're calling let test.
Oh, thank you. Always the syntax. We can write the solutions, but can't write the can't call our functions right. All right. Yeah, if without the quote here, what am I trying to do? Without the quote, what's it trying to do here? Go ahead.
Oh, function name one.
It's trying to apply a function named 1 to the inputs 2, 3, and 4. When you quote it, now it is passing in this as my list of numbers, not trying to resolve the solution of that function call. All right, so there's our 10. Does that make sense? So then, why don't we do this just for practice? I'll leave this let test stuff in here. And let's get rid of this stuff for right now. So I'll give you an easy homework assignment.
Is that sarcasm?
No, it is going to be easy. Should be easy. So we want to sarcasm. I never use sarcasm. We want to move the logic from that guy into apply expression using a let rec. Right? You already have the entire function. There's the function. Move that into your apply expression using a let rec. Make sense? It should be just a couple of copy and pasting and proving you understand how let recs work. See, it is simple. I mean, you got to pay attention a little bit to the parentheses stuff, but okay. So I'll go ahead and I'll paste the current version of the code. For right now, don't test anything with ++. Seems like we might have a bug in there. It might be something stupid. It might even been something I did, but don't test with that. Just solve this part and remind me to fix ++ at the beginning of next class. I will put up the Bible homework today. I've been late. I'll make it due at the end of the weekend. All right. Yeah. So I was sick yesterday morning and just didn't put it up. So I'll give you extra time to make up for the.
Are we at the part where you're picking out the verses or parts?
I don't remember. I have to Google it. At least I'm not lying about it. I would pick out bad ones. At least I think.
We're gonna pick out the last
Yeah, you're right. It's possible you're right. It's possible that I am out now. So, but I know the very last one was still from the list. So, yeah, we'll have to see. I'll tell you what. I'll pick this one out regardless.
Okay.